Hello, Mr. Bong. This is my presentation for assignment 2. Since the content is quite detailed, it's hard to fully explain everything within just 2 or 3 summary slides as required. So I took a bit of creative liberty to use an animation to compress everything into 3 slides for a clearer presentation. Let me start by introducing our site. The project is located next to Bondo University. There are 2 lane roads on the north and south, and the 4 lane roads on the west. The surrounding environment is quite open, with minimal disturbances. About 25 meters to the southeast is the Australian College of Information Technology. Apart from needing to control noise, it doesn't have much impact on our construction activities. Since we couldn't find a borehole log for Robina, we used the solid data from Surface Paradise as a reference. These 2 images show the stratigraphy and the parameters of Surface Paradise. You can see here and here. The first 2 layers is the sand and the stiff clay and the gravel sand, the bedrock. Based on this, we made some assumptions about our own site conditions. I'm in charge of the foundation design for the office tower, so I focused on the east side of the site. Similar to the surface, the top layer are medium to very dense sand, followed by silty clay and the sandy gravel. Below 14 meters, we encounter medium weathered siltstone. The brief mentions a solid strata at 10 meters below ground, but doesn't define it clearly. So we made an assumption that solid strata refers to soil layers with N value above 50. That would be our sandy gravel layer. We also assumed that the soil conditions are relatively uniform across the site, so the risk of differential settlement is low. As for the building itself, we've made the following assumptions. The 20-story tower uses a frame core structural system. The podium is regular frame structure. Floor-to-floor height is 3 meters for the tower level, 4.5 for the podium, and 3.6 for the basement. Now moving on to the side layout. The south side has light traffic and is close to both the east and west construction zones. So we've selected it as the main entry point here. The east side borders Bondo University and has a large surface car park with busy traffic, so it won't be used as an access point. The north side is the University Drive, will be served as the exit. Inside the site, we'll set up a temporary ring road to allow vehicle movement, with the central area used for the site facilities and material storage. Around the edges, we'll place temporary earth stockpiles, material storage, and rebar processing zones, like here and here. All positioned within the tower crane lifting radius. We plan to use 2 tower cranes. The first will be on the south side of the construction zone, this one, and the second one is this. Will be fixed on the podium slab after podium construction is complete, covering the entire tower area. And next part is foundation system design. The basement floor-to-floor height is 3.6 meters, so we expect an excavation depth of at least 10.8 meters. Between the 10 to 40, we've got dense sandy gravel, which is ideal for the bearing layer. Based on this, we shortlisted several foundation types, and after comparison, we selected a flat slab raft combined with pad footings. And here is why. Bedrock is 14 below ground, only about 3 meters below the basement slab, and the sandy gravel is good bearing capacity, and the risk of uneven settlement is low. Pile foundation would be not cost-effective for the project. Isolated footing alone wouldn't suit the tower loads. After reviewing case studies and design guides, we determined that the raft foundation is the practical and cost-effective choice. Here are 2 case studies to support this. The first one is AMP building in Perth, 30-story office building with 2 basement levels, similar in scale and soil condition to our project. The water table is about 2 to 3 below the ground, and the raft foundation sits 8 meters deep on a layer with N equals 45, E equals 230 here and here. Very comparable to our sandy gravel layer with N equals 50, E equals 150. The second one is urban office building in Sydney. It's 155 tall with a 13.3 meters deep basement. The raft sits on the moderately weathered siltstone. The soil is slightly stiffer than ours, and they use a thickened flat slab with strategic use of reinforcement and high-strength concrete. Again, very relevant to our case. So for our project, we adopted the same thickened flat slab raft under the basement. with varying thicknesses based on the load distribution. Since the brief says the basement is 1,000 square meters smaller than the podium, we use isolated footings under the podium areas without basement to improve cost efficiency. Here, isolated footings, and this area is the pad footing. Now onto the shoring system. This project is a deep excavation with high groundwater level, and the waterproofing is critical. After comparing options, sheet piling lacks bending stiffness and risks deformation in dense soil. Contiguous pile walls have poor waterproofing performance, and diagram walls work well but too expensive and time-consuming. Second pile walls are good compromise, strong, waterproof, and more economical. So we choose second pile walls. And for the case study, 26-story office building in Western Sydney, to basement levels, 10.4 meters excavation, similar to ours. They use 1.2 diameter second piles spaced at 1 meters, extending 6 meters below excavation base and 1 meter into the bedrock. Now for the lateral support system, for a deep excavation with high groundwater, lateral support is essential. The two main options are strutting system and anchor systems. We compared both and choose ground anchors since the soil stiffness is high and no underground surfaces or sensitive structures nearby, and anchors don't occupy internal space. And for the case study, an 82 meters tall office building in New Zealand, 14.5 deep excavation, use ground anchors to tie back the shoring wall, similar condition, good precedent. Next one is a dewatering system with high permeability soil and high groundwater. We must dewater before excavation, and at 20 to 13 depths, a deep well system is suitable. We'll place wells 1 meter apart around the pit, and monitor the water table continuously. Excavation can only begin when the water is at least 0.5 meter below the base level. Next one, the construction methodology. We compared top-down and bottom-up method. Bottom-up is the default, but we also explored top-down through case studies to see if it's viable for our site. The first case is the 18 and a 9-story tower in Sydney. The reason is there's no anchoring access available for the western boundaries. In top-down construction, each floor slab acts as the horizontal support, effectively bracing the perimeter retention system. And the second one is the 7-floor group of apartments in Perth. Reason is densely built up surroundings. And the third one is church house in Perth. The reason is top-down construction method provided a high rigidity retaining system, an important characteristic in mitigating risk to the adjoint, the oldest brick building in Perth. After reviewing a wide range of case studies and literature, we have chosen the bottom-up construction method for the following reason. Most projects that adopted the top-down construction method did so due to the site constraints, such as limited space or surrounding structures, which necessitated an alternative to the conventional bottom-up approach. But in contrast, our project site is spacious and free from such constraints. And according to the literature, when the foundation depth is between 12 and 13 meters, there's no significant cost difference between the bottom-up and top-down method in terms of construction expenditure. However, the top-down method involves greater complexity, which leads to higher management and coordination costs. And next one is basement perimeter wall. Since we are using second pile walls, there are two options: pile wall integrated system and separated pile and wall system. Since the integrated walls are mainly used in tight spaces and we've got enough room, we'll go with separated system. Here are some diagrams showing the external wall system and the waterproofing details. We'll seal all wall penetration pipes with a waterproofing sealant, apply waterproofing membrane on the soil facing side here, and apply reinforced membrane at corners, a protection board to prevent membrane damage. Next part, waterproofing system. The waterproofing design for the basement perimeter wall has already been adjusted in the basement perimeter wall design section here. So the section will not be repeated again. Waterproofing at anchors points. At anchor head location, apply cement, water, or water stops to ensure a proper seal and prevent water ingress for the seepage at second pile wall joints. Grouting with cement slurry should be performed from the top of the excavation, waterproofing for the raft slab. After completion of the blinding layer, a fully bonded waterproofing membrane should be applied across the entire surface. At the perimeter, the membrane should be turned up along the second pile wall to a minimum height of 500 mils above the finished slab level, like here. And the raft slab area between the basement wall and the second pile should also be fully covered with waterproof membrane here. Yeah. Now for earthwork excavation, here's the reference case. The office tower in Perth, 38 stories, 7,831 square meters site area, 20 meters deep excavation, very similar soil profile. This is their excavation equipment plan. 2 excavator for bulk excavation, 15 tipper trucks for earth moving, and 4 rock drills for rock breaking. And based on that, I developed an excavation plan for our projects. And the last part is construction process. First one, site preparation, then survey and set out, deep well watering system installation, second pile wall construction. Next step, capping beam construction, layered excavation, stick raft slab construction, and then main structural construction. Last one, backfitting. Okay, that's all my part of presentation. My teammates will now take over and present the remaining sections. Thank you, Mr. Bong.
I will be presenting the slab system and formwork solutions we've chosen for our mixed-use development project. We've selected a raft foundation for both the retail cube and the office tower. For the retail cube, which is a 9.5-meter high, single-story structure, the raft foundation is ideal due to its ability to distribute loads evenly over moderate soil. It also simplifies construction by avoiding deep excavation, which makes it both time and cost efficient. The river is the DFO Brisbane Airport, involves a single-story retail building and a new parking lot. This case shares similar foundation capacity requirements with our project's car dealership, and the building height is also comparable. For the office tower, the raft is also appropriate. For the slabs in the basement, we propose a two-way post-tension slab. We can see the data comparison in the table. This system has a shortened construction timeline and is thinner than a conventional reinforcement slab, reduces concrete usage, and supports non-spans between columns. It's perfect for maximizing car parking and plant room layouts. The Crown Hotel in Perth demonstrates that using post-tensioned floor slabs in the basement of mid to high-rise buildings ensures the sufficient structural load capacity while reducing concrete usage. And our project is in the school area close to the lake. Using the same post-tension slab as the case project can effectively shorten the construction period and prevent pollution. For the podium, we recommend a two-way post-tension flat slab. This enables short construction timeline, a column-free layout, and cost-effective. The case is eco-preeminent environment. The number of floors and overall building layout are comparable to our project, but site constraints prevented the use of large equipment. In contrast, our project has flat terrain and good site accessibility, allowing the use of big equipment to further accelerate the construction schedule. For the upper floors of the office tower, we propose a composite slab using steel decking. This solution speeds up construction and reduces floor weight and allows flexible column grids. It is ideal for the office layouts. And this system has been used in the Midtown Center in Brisbane and 20 Costhouse Queen in Wellington. Like the case, our project requires a lightweight above-ground structure to align with the proposed raft foundation and medium soil condition. For the formwork system, for the basement slabs, we propose a modular panel system with drop heads that reduces the slab cycle and improves safety. And to the podium level, we choose table formwork. The case is mobile in South Brisbane. The podium is planned to use the same type of floor slab, making it feasible to adopt the same formwork system. For the tower slabs, The steel decking itself acts as permanent formwork, eliminating removal time. And for large retail cube, we choose modular panel, formwork with braced edge. The case is Warwicky industrial shading Warwicky. And we recommend modular panel formwork with edge shuttering for the tower wrapped slab formwork. The Australia 108 project in Melbourne used the same system to complete the 2.2-meter deep wrapped foundation. The case building is taller than ours, although the overall foundation type differs. And the system includes wrapped slabs, which is sufficient to meet the construction needs of our building's 1 to 2 meter high wrapped foundation.
My presentation will cover three main parts: the facade systems for the podium level and office tower, structure system for the large retail hub, wall facade and roof system for the retail hub. So let's start with the facade systems. For the podium level, the recommended facade system is a hybrid of glazing curtain walls and metal panel walls, inspired by the Case Queen Street Village project. As the facade distribution drawing shows, glazing curtain walls used at shop front elevation, like in entries, retail display zooms at side and food court areas. The metal panel walls are used for the podium rear elevation, the corners and non-display areas, especially curved podium elevations. I compare the stick system with unitized system. Also, the unitized curtain wall system offers faster installation. It is not necessary for the low-rise podium level. The prefabricated curved facade will take more time and cost. Therefore, I recommend a stick installation system for glazing curtain wall and segmented installation for metal panel. For the office tower facade, I used the K310 Ann Street office building in Brisbane and proposed a full-height glazing curtain wall system installed by unitized system. Compared to the stick system, the unitized curtain wall system offers a significant advantage in installation speed, particularly for high-rise building. And moreover, metal panels can be considered installed on the sides. And moving on to the structural system for the large retail hub, after comparing with the case there for Brisbane Airport and Bunnings Brisbane, and consider about the construction requirements: 10,000 meter square large retail hub, shallow foundation, and short construction period. The steel polo frame will be recommended. The steel polo frame system combines prefabricated structural steel components, including columns, rafters, purlins, and bracing, to achieve a lightweight, stable, and efficient structure. Each element contributes to reduce construction time, improving structural stability and supporting large strain requirements. For the roof system, I propose a low-pitch steel roof system inspired by the Pillow Talk headquarters project. Compare Pillow Talk with large retail hub. The two buildings have similar structure, so the same roof plan will be recommended. We can use color-bound metal roof sheeting, which is low maintenance and corrosion resistant as the building near the sea. Also concealed gutters and downpipes are needed, as Gold Coast heavy rainfall commonly occurs during the summer months. And let's talk about wall system, also a facade system for the large retail hub. These two cases show different wall system. We can see the Bunnings tiled-up wall system and the DFO combined wall system. And after comparison, the tiled-up concrete system was considered heavy and slow. Therefore, I recommended the combined wall system, which provides multiple functions, not only wall system but also a facade system. And the material distribution shown as drawing. It's the same logical with the podium level. I recommend the glazing curtain wall at entries, and also for display. On the other side, use metal panel to reduce the time and cost.